turbo engine running.
Absolute genius.
Get this.
Welcome.
This is the show where we bring you
Science.
What that essentially means is
discoveries,
Advances.
Questions. Research.
technology. Unbelievable.
Without further ado,
This is The Naked Scientists. Hello, welcome to this week's Naked Scientists. This is the show where we bring you the latest breakthroughs in science, technology and medicine. I'm Chris Smith, and coming up this week, evidence that kids born by caesarean section are much less likely to respond to measles jabs, signs that members of the crow family think a lot like we do, and how ancient trees have revealed that last summer was the hottest for 2,000 years.
From Cambridge University's Institute of Continuing Education, this is The Naked Scientists.
First this week, researchers at the University of Cambridge and Fudan University in China have found that the first dose of their measles jab is almost 3 times more likely to be completely ineffective in children born by caesarean section compared to those born vaginally. Henrik Sauge from the University of Cambridge's Department of Genetics suspects that differences in the microbiomes of babies born via the 2 different routes might be at the heart of it. And as measles cases continue to rise around the world, it's a very important health issue to bear in mind.
So measles remains a really big problem around the world. About 130,000 people die each year from measles, and we have a very good vaccine. But for some reason or other, sometimes when we vaccinate infants, they're actually not protected afterwards. And that's always been a bit of a mystery. And so what we did was to try and understand why it is there are these infants, we think they're protected, they're vaccinated, but in fact they're not.
How did you pursue it?
So we worked with a cohort in children. So what that means is right from birth, a group of babies were followed up over time. And so what this team in China did is they collected blood at very regular intervals. They then noted down when these infants got vaccinated. And in the blood, we could then see whether or not they had protection to measles, including before and after vaccination. This allowed us then to identify those infants that actually failed to mount an immune response following vaccination, as well as to carefully monitor how antibodies in general change over time, including from maternal antibodies that's given to your mothers at birth, and also then how your maternals post-vaccine change over time.
Did any of the vulnerable individuals, the one that you were documenting an apparent absence of measles immunity, then go on to catch measles?
No, so in measles generally it tends to have big outbreaks and then you have no circulation for long periods of time. And so in this case there wasn't a measles outbreak, and so fortunately these individuals did not develop measles that we could tell anyway. And also very importantly is, like most countries in the world, in China you have 2 doses of the vaccine, and all the individuals who failed that first dose ultimately got protected with their second dose.
So it's not that you're ruled out if you get vaccinated and you don't respond, you're never going to. It's just a question of you have more and it pushes those stragglers over the immune line.
That's exactly it. And that's something we've generally always known, is that second dose is often just to pick up those individuals who failed that first vaccination. That's certainly the case here as well.
So what we'd like to know is what's special about those people who were the primary first vaccine failures, what connects them, and what might we be able to do about it?
Absolutely, yes. And this is probably true not just for measles, but for many other infectious diseases. So what we did is we just really looked at all possible reasons or hypotheses as to why some people may fail a vaccine and others not, who otherwise look completely identical. And the only thing that came out was the mode of delivery of those babies or those infants. What we found is babies born through C-sections were around 2 to 3 times more likely to fail their vaccine compared to babies born through vaginal delivery. Even though the vaccine is happening many months later, it seemed to have this long-term effect on the ability for you to mount an immune response.
Indeed, we give that MMR vaccine at least a year or more, don't we? In this country, at least. So why do you think there might be that connection to caesarean section then?
That's completely true. And I think there's another whole group of people who maybe don't mount so high an immune response. And that's really to do with this reason we'd waited for a year in the UK. And that is, we have these maternal antibodies which are passed from your mother to the baby. And they're fantastic. They protect you. But they're very good at stopping the vaccine from having its desired effect. So what we do is we tend to wait until those maternal antibodies are very low. And that's why we wait for a year. in the UK and in many other countries too. But this seems to be something completely independent to that. And I think what we're slow discovering more and more is something called the gut microbiome. What this means is all those friendly bugs which help you in all sorts of aspects of your daily life, including the development of immunity. And what happens is that mothers have a vaginal microbiome, which it gets passed on to the infants at birth. And if you're having a C-section, you're completely circumventing that. So you don't have that early microbiome that you would do otherwise.
Some people say that's the most important meal you'll ever eat, don't they? They say your first taste of life is a mouthful of muck, but it's absolutely critical for good health. But how do you connect then what the microbes are doing with response to a vaccine? Because you're still running into all kinds of other infections as a little kid, and they don't seem to behave differently, or do they?
That remains an excellent question and a very, very open question. So we weren't able to really tackle that through this study, and certainly it's something which we will need to focus on more, is what is the mechanism by which all this muck, which as you say we now have from the very earliest stages of life, really develop or allow you to develop immune responses going forward. It seems to be relevant not just for measles, but really all those different vaccines and all the different infections. And what's really comforting is that those individuals who were born through C-section failed their vaccine. They ultimately did respond. So all it is really, I think, that's happening is taking longer for you to develop the appropriate microbiome. So certainly you don't want to be too worried that in the long term you won't be able to mount an immune response, but it just takes a bit longer. Another point to note is that in the UK, we wait until 3 to 5 years for the second dose. So they're really, and we're having increasing rates of C-sections. About 3 in 10 babies are born through C-sections these days in the UK. So it might be that from a policy perspective, we might want to consider shortening that for infants born through C-sections.
Because epidemiologists have connected other health outcomes to caesarean section as well, haven't they? Things like a greater risk of allergy in later life, more risk of getting gastrointestinal problems as you get a bit older. So there does appear to be something going on. How are you going to try and pursue this then? Are you going to try and get underneath what that connection is between what's going on in the gut and how the immune system is maturing?
That would be wonderful, yes. So I think there are a number of ways you can continue this study, and we will certainly do so. One is really better characterization of this microbiome, both in the mother and the baby, and seeing how that develops in the first few weeks and months of life, seeing how it changes then following vaccination, following infection, and I think that will give us a more complete picture. At the moment, this is really ultimately an observation. We see some babies that fail their vaccine, and we just see how they're different from ones that don't. But now what we need to do is do some more detailed studies that really try and understand why.
Henrik Sauge there from the University of Cambridge, and that study just came out in the journal Nature Microbiology. Well, more fascinating research from Cambridge University now with a new study on the ability of Eurasian jays, these are members of the crow family, to remember incidental details of past events. The findings, which have just been published in the journal PLOS One, suggest that these brainy birds have memories that work very similar to our own. To find out more, I went to Clare College to meet Nikki Clayton, Professor of Comparative Cognition at the University of Cambridge.
So a long time ago now, I showed that jays are able to experience the past. That is, they don't just remember information about what's happened. They're able to project themselves in self and time to remember what happened, where and when. And that was the first demonstration of what scientists called episodic memory. You could think about it as experiential memory. You don't just know a fact about Clare College, the second oldest college in Cambridge. You will have an experiential memory of our conversation sitting in the SCR in Clare on this gorgeous sunny day. So that's an experiential or episodic memory.
So that would be like every time I come to Clare College, the sun shines. So next time I go to Clare College, I won't take my raincoat and I'll wear a T-shirt. That would be an example of that kind of associated planning for the future based on an experience in the past.
Absolutely. That's exactly what it's about. If you think about it, as Lewis Carroll said in the series of Alice in Wonderland and Alice Through the Looking Glass, it's a poor sort of memory that only works backwards. And if you think about it, what's the point in remembering things if you're never going to need to use those memories again? But really, experiential memories, not facts about the world, these experiences, evolved with the future in mind because you use them in the here and now to think about the past in order to plan for the future. Hence your example of the sunny day and no need for an umbrella and just wear a T-shirt.
So what have you done to push that further?
So what the recent experiment is on is about Jay's memories of the past, their experiences, and the first author on the paper is my PhD student, James Davies. And the idea was to think about whether they could remember other aspects about the event, because one of the hallmarks of experiential memory in people is that we don't set out with an agenda of things to remember. We just experience an event and then we remember things about it. And so the idea was that maybe we shouldn't just be asking, can they remember what, where and when, but can they remember other incidental features about the event?
So that would be like, I came to Clare College to see Nicky Clayton. I remember that, but I also remember I was wearing a red jumper at the time.
Exactly that, or that you were sitting on a red sofa. And there was no reason to remember that. It doesn't really help your memory of the event in any particular way, but it's just these unexpected things that you just happen to remember.
And you wanted to know, do the birds do that like we do?
Yes, we wanted to know whether they could incidentally encode these features, not features that they deliberately needed, but whether they just happened to remember them by chance. And when I say we, I mean my PhD student, James Davies, my former PhD student, who's now a professor at the National University of Singapore, Elias Garcia Pellegrin, and myself. And I just want to make sure that they get credit too. I don't want you to think it's all Nicky Clayton and nobody else is important. And of course, I must give credit to the gorgeous Eurasian jays, because without them, none of this would have happened.
How do you do that then? How do you get a bird to remember the red jumper as well as where I hid my lunch?
Well, what we do is we give them various little pots that they can hide food in, or the experimenter can hide food in. But the pots have different patterns or colours or shapes on them. And those features are incidental to the task. They've just got to remember which cup had food, where and how long ago. But these features are irrelevant during training. They're nothing to do with it. Then we ask them afterwards, but did you remember? So you might imagine, rather than a jumper, there's a tray with particular patterns on it and the cups are on those. Can they remember the pattern on the table where the cup was?
And do they? Do they store that incidental information alongside the other things they were trying to remember?
Yes, they do. So it's often called the unexpected question because they're not being trained that this is the question. They're being trained, they need to remember what, where and when. They're not being trained about your red jumper or the patterns on the cups or trays, and they just happen to remember it. So that shows that this is another feature of experiential memory that they share with us. They seem to remember their personal past experiences in the same way as we do, and that's why it's important.
And apart from the fact that they appear to share that memory trait, what else does this tell us about how the birds are thinking?
Well, it's just one more thing in this clever cognitive toolkit that these members of the crow family have. Their brains relative to body size are as large as those of chimpanzees, and they seem to be able to do all the same kind of cognitive feats, experientially remembering the past, wait for a better future reward, being able to imagine the future and think about what others are thinking. And that's why we call members of the crow family, including these jays and ravens and magpies and crows, we call them feathered apes, because when it comes to their cognitive abilities, although they have feathers and not hands, they seem to be as smart as chimpanzees.
Nicky Clayton there.
The Naked Scientists podcast is produced in association with Spitfire, cost-effective voice, internet and IP engineering services for UK businesses. Find out how Spitfire can empower your company at spitfire.co.uk.
Music in the programme is sponsored by Epidemic Sound, perfect music for audio and video productions.
You're listening to The Naked Scientists with me, Chris Smith. Still to come, how have researchers worked out that last summer was the hottest for 2,000 years? That's on the way. But first, When people say that things are up in the air, that's often a bad sign. But not this week, because the UK has successfully completed flight trials of an advanced quantum-based navigation system that can't be confused or jammed by hostile states. In fact, it's so accurate that it means that even if GPS signals are lost for extended periods of time, it can still keep track of location. To find out more, I caught up with Ramsey Farragher, who's a fellow at Queen's College in Cambridge and a fellow of the Royal Institute of Navigation. First, we talked about how present-day GPS works and how it can be vulnerable.
The main tool that we all use, whether we're a person on the way to the shops or whether we're a submarine captain or a fighter pilot, we rely very heavily on the global navigation satellite systems, of which GPS is the most famous. So these are a lot of satellites that orbit the Earth. They transmit radio waves down to us here. We have little receivers in our smartphones, in our cars, and in our submarines and fighter jets that use those radio signals to work out where you are and when you are. They're a meter-level accurate positioning system and a nanosecond accurate timing system.
And how does my GPS receiver, whether it's in a phone, it's in my car, how does it know where I am?
Fundamentally, they are atomic clocks in space that transmit the time. And because the speed of light is constant, when you are different distances from each satellite, you get those copies of time at slightly different times. So you collect up these numbers from the satellites and you do a little bit of maths that calculates, in order for me to have picked up this particular sequence of the time from these particular satellites, I must be at this location on the Earth's surface. And we've become very reliant on these signals. And because these signals travel a very long distance to get to us, 20,000 kilometers to get to us, if you have a nearby jammer, which is just spraying noise out on the same radio frequency, it completely blankets the signal and it removes the ability to use GPS anymore.
Are they vulnerable as well? If someone were to create false signals, could it be fooled into thinking you're where you're not?
Yeah, that's called spoofing. And it used to be just the realm of Hollywood movies. There was a James Bond film all about spoofing GPS. Nowadays, unfortunately, it's possible to download software on the internet and buy a cheap little software-defined radio and actually spoof your own GPS. And people do this to cheat at Pokemon Go and to do research into GPS and to test GPS receivers in smartphone companies and car companies and things before they ship them in the products. So it's an unfortunate feature that in order to test these systems well before we give them out to the public, we design them so that they can be spoofed easily so that they can be tested well. So it's a difficult catch-22, but yes, it is easier than we would like for people to broadcast fake GPS signals into receivers and trick them into thinking that they are somewhere where they are not.
And the new system that they're now testing, what's the vulnerability that that's designed to protect against, and how does it work?
So because GPS can be jammed, it can be spoofed, and it can simply be blocked. If you drive through a tunnel, for example, the signals can't penetrate through the tunnel covering. We use what are called inertial sensors to bridge those gaps. And this consists of a little box containing accelerometers and gyroscopes. And when the GPS signal is unavailable, the accelerometers measure your changes in acceleration, the gyroscopes measure your changes in heading, and you can keep adding up the measurements from them to work out how you've moved since your last GPS fix. Your smartphone has little accelerometers and gyroscopes in it as well that are predominantly used to play games and to make the screen turn when you turn the phone. But even the tiny, cheap accelerometers and gyroscopes inside your phone can do a really good job of bridging GPS fixes for, say, 10 seconds. So this new quantum navigator is a much, much more accurate and sensitive accelerometer and gyroscope set than we've ever had before. And so that means you can survive very big GPS outages, maybe hours.
How does it work?
It uses cold atom interferometry. And so a chap called Bose, who's less famous, and Einstein, who we all know, they wrote a seminal paper a long time ago on how if you cool down atoms enough, they enter a new state called that we call a Bose-Einstein condensate. What happens is all of the atoms of the gas collapse down to a single energy state, and they all now start to act as waves instead of particles. And so because they're now at the quantum limit where they can all be treated like waves instead of particles, you can do wave stuff with them, like interfere them and diffract them and make use of their wavelength, which atoms don't normally have the concept of a wavelength until you bring them down to this point. And the wavelength of these cold atom systems is about 10,000 to 100,000 times finer than the wavelengths of lasers. And so the laser-based gyroscopes we've been using for years are about 100,000 times less accurate than these ones. So it's very exciting. That's why we're using the new technology. It's a whole new level of sensitivity and performance.
How big is it though, Ramsey? And is this easy to do, easy to build, easy to apply? Because the report I read was a whole bank of material and equipment on aircraft.
Yeah. So I had the pleasure about 15 years ago to go and visit early work in Imperial College in London on these cold atom interferometers. And I was pretty much stood inside the device at the time. I was inside a lab where the entire room was dedicated simply to trapping, cooling, and using these atoms. And so there were lasers everywhere and power supplies and lots of tubing and piping. And it's still kind of container-sized, from what I gather of some of the experiments that have been going on. But the aim is to get tabletop and eventually kind of shoebox-sized versions of these sensors.
Can they cope with going around corners really quickly, though? Because aircraft, it's not the gentlest experience. And if you're a military aircraft, these guys are going to be pulling multiple Gs to take evasive actions and so on. How do their clouds of cold atoms cope with that?
Yes, that's a very good question. So the different designs, the different types of accelerometers and gyroscopes that we've used over the years all have different levels of sensitivity, accuracy, and dynamic range, which is how big a force they can survive and still operate. And at the moment, the cold atom technologies don't have high dynamic ranges. It's literally a cloud of atoms, tiny little cloud of atoms, that's being thrown up and down inside a tube. And so if you're midway through chucking these tiny little atoms up and down the tube, and then you give the tube a big kick, they all smash against the side of the tube and you can't measure them anymore. And so this is the current problem that they'll be working on overcoming. And there's various ideas on combining the cold atom technologies with traditional technologies so that when the cold atoms are available, you've got all of that high accuracy, and in high dynamics, you freewheel on a normal inertial navigation system. These are the mere engineering challenges, Chris. Us physicists don't worry about such things.
The man who never loses his way, Ramsey Farragher at Queen's College in Cambridge. We know that the last few summers have been very hot. But how hot? Well, Ulf Bungen's team at the University of Cambridge have developed a way to extract climate data from the growth rings of trees, including even ancient fossilised wood buried in the nearby fens. And these are allowing them to look back over thousands of years, and critically, well before thermometers were invented.
The main message of this paper is that the last summer, so the summer of the year 2023, is the warmest summer of the last 2000 years, and we know that not from instrumental measurements. We are using tree ring data, so a tree is recording for us the temperature over the past 2000 years. And you may now ask, how do you get 2000-year-old trees?
How do you get 2,000-year-old trees? No, I was just going to ask exactly that. So where did you get the trees from, and how do the trees record temperature? I know you're saying you're looking at the rings, but what about the rings records the temperature?
There are basically no trees, almost no trees that are 2,000 years old. So we take living ones for maybe the past 300-400 years, and then we extend the information of these living trees with relic wood, with dead material. So we, for instance, would go into the college here in Cambridge in the roofs and take samples and collect material from historical construction timber, or we working together with archaeologists that have excavations where we get wood remains out, or we are spending lots of time, for instance, just last week I was in the Fenland north of Peterborough, where we collect subfossil relic wood that comes out of the peat bogs. And all these different wooden sources help us to build a continuous time series, so we call that a chronology, that covers now 2,000 years for different parts of the world. And how do we do that? Or in fact, how are the trees doing that for us? So these trees are almost functioning like a thermometer. So small changes in summer temperature are reflected in wider or narrower rings. So the tree is suffering if it's getting too cold, and the tree is thriving and producing lots of wood under favorable conditions. And then we have an overlap where we have both the instrumental measurements. Whenever we have an overlap of what the tree rings are recording and what we measured with instruments, we can build a model. We are calibrating, we are trying to understand what does it mean if a ring is wide or narrow, and how can we transfer that into temperature.
Could anything else, though, affect those tree rings? Is it just temperature, and is that discrete, or could, say, a very wet year make a difference, a very dry year make a difference, and therefore other things could tweak the formula?
You will be surprised about the answer. Everything affects the tree. So when a tree grows, it's completely affected by a lot of things in its environment, and that is all recorded. But we are not relying on a single tree. We average the information of hundreds or even thousands of trees. And then we are cancelling out the noise. And then what we emphasize is a common signal. And if we see that a tree shows a narrow ring, let's say in the European Alps, and at the same time, in the same year, in the same summer, also in northern Scandinavia, and so on, over a larger geographical region, then we know it can't be a local factor. It must be a larger forcing factor, and that is then temperature.
And how much bigger are the effects now? So the tree rings are saying it's warmer now than 2,000 years ago. How much warmer?
The trees are only recording something that happens during their growing period, right? That is the summer, let's say from spring to autumn. The Northern Hemisphere summer temperature of 2023 was roughly 2 degrees warmer than the pre-industrial period. Before our study, people just had information from 1850 to 1900, which we call the period of early instrumental measurement. So that is where in some places of our planet, certainly not everywhere, we had the start of early instrumental measurements. These measurements were also biased. They were not absolute accurate. They still had to learn how to build up meteorological stations, to fine-tune that and so. And based on this period before industry starts, significantly in the 20th century, we would say we have this 2-degree warming trend. And now with the tree rings, we are now able to provide and set the most recent anthropogenic warming in a much longer context. And that is the main achievement of this study. So it makes a huge difference if you say the last summer was the warmest summer of the past 150 years, or if you say the last summer was the warmest summer of the past 2,000 years.
Ulf Bunchen from the University of Cambridge, and that study just came out in the journal Nature. Well, now it's time to get our teeth stuck into some theoretical physics, and James Titko has taken on this question of the week.
Thanks, Chris. This week's question comes in from listener Daniel.
Hello, my name is Daniel from Norwich, and my question to the team is, how do we know for sure that the laws of physics that humans have set down in ink are the same laws of physics that another civilization might have on another planet? Thank you.
I know just the person to ask for this one, never one to shy away from the big questions. Here's Toby Wiseman from Imperial College London.
Does physics change as we move around the universe? One of the fundamental tenets of cosmology is in fact that we don't live in a special location. All locations and all directions are the same. And that is absolutely what is observed when we look out into the universe. Our modern theory of cosmology uses our theory of particle physics, which we derive from collider experiments such as CERN on the Earth, and then our theory of gravitation, Einstein's general theory of relativity. Now, it isn't a complete theory, but if we are not worried about physics in the very earliest epoch of the universe, then the theory is remarkably good. We can understand everything that happens within this theory from way earlier than a second after the Big Bang. You start with this almost blank canvas of the Big Bang with little quantum fluctuations on it from what we call the theory of inflation. And those quantum fluctuations grow, seed, structure, because of gravity pulling structure together. And then eventually this forms the galaxies, stars, and so on that we see today.
I think Janus's comment on our forum post for this question captures what Toby is saying about some of the unanswered questions we have and how they fit into our understanding of the universe very nicely here. They write, "It would be possible for another civilization to have pierced the veil more deeply and have a better understanding of some of those principles than we do. This would not constitute a change in the rules, however, but just a better understanding of what they are."
If you're sitting on a particular star somewhere, you may look down at your star and call it a different name, and you may look at the elements in it and call them different things. But this theory really predicts all of that physics. It has all of that physics in it. And we think of this theory of the standard model of particle physics together with gravity as something that we've discovered and uncovered rather than something we have constructed. The fact that we can write down the theory of all the forces and all of matter on a t-shirt in a couple of lines is astonishing. And it's a process of uncovery. We've got closer and closer, and the theory in many ways has got simpler and more elegant as we've honed in on it. It's very difficult to understand how that could be a human construct. This is the most accurate thing that's ever been predicted by any theory of anything, and it works. That's where my money is anyway.
If it's good enough for you, Toby, it's certainly good enough for me. A mesmerising and humbling answer from Toby Wiseman from Imperial College London. Thank you to him and also to Daniel for that question. Next time, from the theory of everything to the theory of frothy coffee, it's Thomas's turn to ask this question.
Hi, Naked Scientist. I heard the milk foam we make for our cappuccinos consists of denatured clumping proteins. If I heat up the milk for my coffee for a bit too long, it forms a skin. And after removing that skin, I can still make pretty nice foam from the milk. How come? Shouldn't the lack of protein prevent the formation of proper foam then?
Thank you, James. And if you'd like to get involved, do please feel free to join in the conversation over on thenakedscientist.com/forum. And also you can drop us a line if you have a question or an answer you'd like to contribute. It's chris@thenakedscientist.com. Just before we go, we do rely very heavily on donations to keep the show on the road here at The Naked Scientist. So if you're able to support us, we would be very grateful indeed if you could pop over to nakedscientist.com/donate. Every little helps. That's all we have time for this week. Do join us on Tuesday when we're going to be examining AI, artificial intelligence. How does it work? Where's it heading? And do we overestimate its capabilities? The Naked Scientist comes to you from the University of Cambridge's Institute of Continuing Education. It's supported by Rolls-Royce. I'm Chris Smith. Thank you for listening. And until next time, goodbye.